So let's look a little closer at the shape of the black body curve. Let's first of all be careful about what we're graphing here. We're graphing intensity per unit wavelength on the y-axis and wavelength on the x-axis so that the area under the curve, which we call R, is equal to the integral of the intensity per unit wavelength times d wavelength. So that's just the area under the curve. Okay, so we're going to talk about this formula in a little bit. This shape, right, in physics we want to be able to explain what's going on with physical laws, and the shape wasn't well understood, and this is the problem. This is the problem, turn of the century, 1900-ish, that the black body radiation curve shape wasn't understood. It was empirically understood, empirically described. So empirically, right, experimentally, people could describe this. And what was found was that this intensity the wavelength maximum, the intensity maximum was wavelength dependent in such a way that, in other words, right, the intensity maximum for this let's say this curve, this smaller curve might be for a light bulb. This larger curve might be for the sun, right? The sun's got more intensity than the light bulb, so it's got a larger area under it. But also, because the sun is hotter, what we find is that a maximum moves to a lower wavelength. And Wien's law, W-I-E-N-S, Wien's law is an empirical law that tells us about the relationship between the temperature of the body and this wavelength maximum. So this is called lambda max, right? This is called lambda max. And we know that this body is hotter than this body. In other words, temperature goes up as that lambda max goes to a lower lambda, or the temperature goes up as the peak gets larger. That's just a hotter body, right? Again, the big peak, this might be the sun, and this is messy, sorry. This might be a light bulb. And Wien's law tells us lambda max times T times the temperature of a body is equal to a constant. And that constant measured to be 2.898 times 10 to the minus 3 meters times kelvins, right? Because this is meters times kelvins. Empirically, there's also the Stefan-Boltzmann law, which is trying to describe the shape of the curve. And the Stefan-Boltzmann law, they find that R, and let me just talk about these units again, right? Remember that I is intensity per unit wavelength, lambda is wavelength, so that the integral of I, and it's written as a script I because it's not strictly intensity, it's intensity per unit wavelength. So the integral of I d lambda would be a total intensity, which an intensity is power per unit area. So R is power per unit area. The total power per unit area of the body, right? So again, if the big curve is the sun, the small curve is the light bulb, the total power per unit area emitted by the body is the area under the I versus lambda curve. That's R, the total power per unit area emitted. Okay, so Stefan-Boltzmann law gives us an empirical relationship, but for the total power per unit area emitted, and it's found that that the total power per unit area, sorry, I said equals, but is proportional to T to the fourth, the temperature of the body to the fourth. So these are our two empirical relationships. Wien's law, lambda T is equal to constant, and Stefan-Boltzmann law, R is proportional to T to the fourth. Going farther with the Stefan-Boltzmann law, just to be specific, we can go ahead and measure that the Stefan-Boltzmann law. We can go ahead and measure the constant of proportionality. It's called sigma. And real quick, let me just go back and say that this constant here, that doesn't have a name for whatever reason, but this constant of proportionality here does have a name. It's called, Stefan's constant, right? It's called Stefan's constant. It's called Stefan's constant. Stefan's constant, and it is equal to 5.67 times 10 to the minus 3 watts per meter squared Kelvin fourth. That's what the units better be, right? Because if R has units of power per unit area, that's watts per meter squared, power per unit area. So therefore, you divide that by T to the fourth, and you get watts per meter squared Kelvin fourth. Okay. Let's say we have a 100-watt light bulb as an example, and let's look at the radiation curve of the 100-watt light bulb, the intensity per unit wavelength versus wavelength, and it looks something like this. The total power per unit area is the area under the curve. And just to note that this is one of the problems with a incandescent light bulb, the kind that have the filament that burns, is that the visible spectrum is really over here, that most of the light bulb energy is in the infrared spectrum, right? So that's visible. And whoops, I went a little far there. The energy emitted by the light bulb is in the infrared. This is the problem with incandescent light bulbs, and it's why today we mostly use fluorescents and LEDs, because incandescents waste so much energy in that infrared region. Okay, so let's just say that we know that a incandescent 100-watt light bulb burns at about 2,700 kelvins. That's pretty hot, right? The surface of the sun is around 6,000 Kelvin. So an incandescent light bulb, pretty hot. That would be the temperature of the filament. And so let's ask the question: what is the temperature of a similar? Oh my goodness, sorry. Of a similar sized 40-watt light bulb. We're just going to use a way to use the Stefan Boltzmann law to answer this question. If I know the temperature of a body given its temperature of an incandescent light bulb, 100 watt, given its temperature 2700 K, we can then use the Stefan Boltzmann law to find the temperature of a similar sized 40-watt light bulb, simply by saying that the power of the 100-watt light bulb, which is equal to sigma, the Stefan constant, times the temperature of the 100-watt light bulb to the fourth. That's an equal sign. The power, I wrote a proportionality sign, it should be equals. The power of a 40-watt light bulb is the same thing where we have the temperature of the 40-watt light bulb to the fourth power. And we can simply take those two equations, divide one by the other. We don't even need to know the constant. All we need to know is the proportionality. And we have 100 watts over 40 watts equals the temperature of the 100-watt light bulb divided by the temperature of the 40-watt light bulb, all raised to the fourth power. Pretty straightforward. And so therefore, if we know that, and I didn't plug in the temperature of the 100-watt light bulb here, even though I know it, 2700 K, just to show the proportionality, we know that the power of one object over the power of the other object equals the temperature of one divided by the temperature of the other to the fourth power, because of this Stefan Boltzmann fourth power law. Or we've got 100 over 40 equals, we just plug in the temperature of the 100-watt light bulb, and we can find that the temperature of the 40-watt light bulb therefore equals 2147 K. Notice that even though the power is 2.5 times smaller, the temperature is not really that much smaller. It's still pretty hot. All right, so then let's ask about that light bulb, about either of those light bulbs. What is the color of the light bulb? What do we mean by what is the color of the light bulb? Well, if the primary color of the light bulb is going to be where the center of that peak is. Remember the peak of the black body radiation curve, right, where the center of that peak is. Whoops. What I want to know is what is the peak wavelength of the 100-watt light bulb. Okay, so the peak wavelength, we're just going to use our relationship for the peak wavelength, or lambda max. Lambda max T is equal to 2.898 times 10 to the minus 3 meters times kelvins. That's not millikelvins, that's meters times kelvins. And so just solve for lambda max, plugging in the temperature of 2700 K. And so what we end up getting is lambda max, solve that, put in your calculator, we get 1.07 times 10. Sorry, keep on doing this. Done this lecture once before, and then my iPad deleted it, so I'm doing it again, but I already had the stuff written down, and I keep on by accident fast forwarding through the stuff that I wrote down. Okay, anyway, don't worry about that. 1.07 times 10 to the minus 6 meters, which when we talk about wavelengths of light, we often put it in nanometers, so that's 1070 nanometers. So think about what is 1070 nanometers. Remember, this is the light bulb, this is the 100-watt light bulb. 1070 nanometers, remember we can go back to the previous page, That's the center of the light bulb peak, which looks like it's in the infrared, and indeed 1070 nanometers is in the infrared. Red is about 740 nanometers, so that's the right end of the visible spectrum is red, right? It goes blue to red, or Roy G. Biv going in that direction. So this is the red end, and so 1070 is in the infrared. And so that makes sense, right? And that's what we were talking about with the light bulb, is that the light bulb has most of its energy, its peak energy is in the infrared, which is why we don't like incandescent light bulbs, because they waste a lot of energy. Unlike the sun, which is hotter, and according to these two laws, that means that the sun is going to be this one here, the higher peak, right? It's going to have more energy, more power per unit area. Certainly the sun has more power than a light bulb. But it's also hotter, and so it runs because of the relationship lambda max t equals a constant. Because it's hotter, because t is bigger, lambda is smaller, and so the sun's peak is actually in the visible. Let's see how that works. So we can just talk about the sun. What is lambda max of the sun? And we can just go ahead and plug in the temperature of the sun, where the temperature of the surface of the sun is about 6,000 kelvins, and simply plug that into the equation, and we get 483 nanometers. It's pretty straightforward plug-in. 483 nanometers. What is 483 nanometers? Right, 483 nanometers is in the visible. It is actually the blue-green end of the visible. It's sort of it's close to the center of the visible, center to left. So most of the sun's energy, the maximum is in the visible. Hence, somehow, we evolved to be able to see the sun, because the sun is the star closest to Earth. And yes, the sun has a large amount of energy. Let me change the color of my highlighter here to something. Whoops, that's not useful. A green highlighter. The sun has a large amount of energy in the infrared. We know that. It's also got a fair amount of energy in the UV, ultraviolet, right? We know that there's some energy that is kind of unsafe for us in the UV, and it's got the maximum is in the visible. So it's got a lot of hot infrared, a fair amount in the UV, but the max is in the visible. Okay. Okay, so we'll stop there and then pick up again on the model. So now what we want to do is we want to model, I know this is kind of messy, let me just draw another one. We want to model this curve. If that's my I versus wavelength, and my curve is sort of like that, what the scientists want to know is why the curve looks this way. So we need to come up with a model for it. And that model is called cavity radiation. We'll start that next time.